Let me show you. Yeah. I have this.
Hi, everyone.
Yes.
Thank you for having me here. The topic of my talk is multimodal deep learning with an application to folk art recommendation. By way of introduction, I'm basically an associate professor at the Department of Management Science and Systems at the State University of Buffalo at New York. And to give you a brief history of, or a little bit of a background about myself, I graduated with my PhD from the University of Maryland, and I've been working in machine learning and data mining and AI for since really my graduate school. So that's almost more than 25 years now. And I primarily work in the area of distributed optimization, large-scale distributed and parallel mining. And more recently, I work at the interdisciplinary research on because I do cross that into operations research in my role in my current job. The primary focus of my research is a very narrow area of AI, which goes by the name of consensus-based machine learning. And that has to do with how you develop algorithms for IoT devices and the Internet of Things. We will not talk about much of that today, but if that is of interest, we can certainly have a chat after my talk here. So, and my research has been funded over the years by the National Science Foundation, by grants from both University at Buffalo and Columbia Engineering, where I used to be for almost 7 years, Amazon, and various other foundations. But today I'm going to talk about a project that involves what's called digital humanities. And in other words, it's really developing an art recommendation system for an endangered art form. And we call it, it goes by the name Chitra Anushandhan, and that's really not an English word, but has its roots in the art form that we are trying to index and search. So why bother about this? Well, it is a very interesting project because we are trying to do an art conservation project from South Asia, in particular from India. So it's really a collaboration between the South Asian Studies Program, Computer Science, and Operations Research. So it's a very multidisciplinary work and involves collaboration of my colleagues from the Department of Anthropology, Art, Computer Science, and Operations Research. The goal is to build a recommendation engine for folk art. And this is a very narrow domain here. And in fact, I'm going to show you very soon why this is an endangered art form. We have in a particular region of India, which in a particular state, what are known as wandering minstrels, who really take scrolls and go around town talking about local events, talking about mythological events. And these scrolls are also accompanied by songs. And it turns out that the South Asian Studies Program is very interested in both collecting this, as well as both collecting the scrolls, as well as documenting evidence of how the lyrics of the song and how they are preserved and so on and so forth. So we got the American Institute of Indian Studies, as well as the National Endowment of Humanities, to get interested in this project for digital humanities, and they ended up funding a fellowship for me. And so at the moment, I am on that fellowship, and we are basically, I'm going to give you an update on where we stand in terms of building this recommendation engine, which really involves developing a large-scale system for art recommendation using deep learning as well as various other techniques. So what am I really talking about? And so I have a little video clip, which I hope that I will be able to open up here. So this is really from field research. And before I start playing this on my system here, if I unmute here, so I'll let you hear a little bit of this clip here, which happens to be this person that you see on the screen now is in fact a wandering minstrel that we actually went down and visited the person. So he has these unique instruments. So he plays a song as well as sings, and there is a scroll which actually depicts the lyrics of the song as well. So I'll let you listen to a little bit of this. There might be some feedback and so there is a little bit of feedback, so I'm not going to be able to show you the full video here. But basically what you saw there was a wandering minstrel from whom we collect both the scrolls, and one of which is actually also depicted here, as well as the lyrics of the song. And these are really very old people, and also sometimes it's an endangered art form. So we really have to do a lot of field research to actually get in touch with them. But then we develop a database where we have both the paintings as well as the scrolls and information about the musical instruments all stored up. So what kind of data are we really collecting? Well, there is the original scroll, and these scrolls could be anywhere to 15 feet or more long. So they're huge. So you can't really get one shot of the whole scroll sometimes. So what we do is we take panel by panel pictures, and from these panels, so here you see a very long scroll, which has been cut up into smaller panels for extraction of images. And from these, we will then connect to audio databases, transcripts of song, textual databases, and so on, which basically stores both the image information and a lot of, so it stores the image as a JPEG file, and it also stores the text of the song, the transcripts of the song, because some of this is non-English. And so we have to we really have to translate it into English and then do the indexing and search here. So this just gives you an idea of the scale of things, because from a given scroll, and here's another close-up of that, we not only do a transliteration from the original language, which in this case is Bengali, and we then translate it into English. So we have the original text of the song, the audio, the video to go with it. So you can really see that there's a lot of what we call multimodal data. And by this, we mean that different types of sensory information, so typically vision, sounds, etc., are actually collected from our environment. And this was done in field research. And then these different types of data go by the name modalities. And multiple modalities are used because it gives us a better intuition of the world that we are trying to model. Because in this case, not all of the first of all, this is a very endangered art form. So there is no other place which we know of that actually stores the lyrics of the song. There's no other place we know of that stores the audio or the video data. So one part of it is actually building out the whole database of this very large, complex multimodal data. But beyond just the data collection piece, what's really crucial is that we develop techniques for that integrate this multimodal data and be able to learn from it, so that when, for instance, somebody else who has an interest in this domain is able to search for a certain type of scroll, he or she would get a proper indexing. So just to give you an idea, Google searching will not work very well at all on this, because the sort of words that you use will not index onto these images, because these are private proprietary databases that at the moment we have with the UV libraries, but it's still not released for public use. So the system architecture that we have is sort of like this, that we have textual databases, and from these large-scale text databases, and for now you can assume that these have been translated into English, we get the lyrics of the song, and we use the English text to extract what are known as features for learning in learning models. And how we do that is very simplistic features. So we use something called bag of words representation. We know we can do much better here, so we can go ahead and do, for instance, various sorts of word embeddings. For those of you who are familiar with these kind of textual databases, we also extract pixel by pixel values for each of the images from the scrolls that we collect. That gives us the representation of the images that we have. So, for the moment, our system actually works only with images and text, but in the future, we actually plan to build out something which will incorporate both the audio and the video data as well. So once we've created the textual representation as well as the feature representation, we have various kinds of user reviews and ratings about each of the panels. So remember, a scroll is 15 to 16 feet long. And so the annotators really annotate a like or no like or don't like for each of these smaller panels, panel by panel information. We integrate all of them to form a large corpus. And this is the corpus that we do our machine learning and AI on. So what are we trying to learn actually? Well, given an image or a panel of the scroll, or a panel of the scroll, and its associated lyrics of the song, we are trying to frame very simplistic questions as of now, things like, are there mythological characters in this particular panel that you are viewing? Are there trees in the diagram? So for instance, if you looked at this scroll, you would probably say that there isn't a tree, but you would say yes to, are there animals in here? But if you looked at this, you would notice there is a tree. So we are trying to do object detection from this, but this really doesn't have a mythological character in it. So some of the concepts that we are trying to learn from these scrolls, as well as the associated text and lyrics of the song, are mythological characters, trees, or the presence or absence of animals in a given scroll. And to elaborate on that, we did employ a lot of humans to actually do annotations for us. And they basically looked at these scrolls as well as the textual data to tell us more about whether they thought what the humans felt about mythological characters, trees, and animals, presence of these in the scroll. Now, we did use something called Krippendorff's alpha, which is an industry standard, and it's used as a reliability coefficient among coders. And they looked at, so what this means is, let's say there are 100 annotators. They would look at a scroll and agree or disagree on whether a mythological figure exists in this panel. And so the degree of agreement on mythological figures is actually quite low. It's about 0.6. And the reason that happens is because we differ on what we mean by mythology. People have different backgrounds. So learning the concept of mythological figures was really hard. But it was much easier when we tried to learn trees. And surprisingly, animals were difficult to detect as well. So in terms of feature extraction, what we did was we basically relied on pixel-based features. We also tried to extract regions of interest. So from your panel, we would try and draw a border around, let's say, a tree that existed in our panel, and then extract features from that. This results in very, very high dimensional data. And the use of these features and the labels being the concepts we are trying to learn, is then used to learn whether there exists a mythological figure, a tree, or an animal in our system. So to present some results from our initial multimodal analysis, and this multimodal analysis only has to do with text and images, we found that our deep learning models here were somewhat better at learning certain kinds of mythological figures and perhaps trees and animals, but we had a number of difficulties resulting from the modeling task. And you will see that the same thing is reflected here. The accuracy of our methods are sort of on the lower side. And the reason we believe is these are very simplistic models. So we don't use, we individually so this one uses only features generated from the text. So you would look at only the textual representation of the lyrics of the song, and you would try to do a search for a given item and see how well your search method went. And the results that you see here do tell us that it's not quite easy to identify animals from our repository if you used only text features. Notice we are not using image-based features here. But in the previous one, this was only from images. So we did an experiment where we extracted features only from images, only from text, and then combined them together to see what would happen. And here we are using just a logistic regression as our model. And so it's not even deep learning. Surprisingly, when we use a very simplistic model, which is sort of the state of the art, you would notice that with combined images and text, we actually don't get very good results. So if you notice, the green one on the rightmost end really shows that it has the lowest. So on the y-axis is accuracy. So we have the least accuracy on the combined effort, which means that we are probably not doing or utilizing all of the data that we have very well. So then we went about and said, well, what can we do to actually make use of the various different modalities that we collect, and then try and build our search engines on that? And so challenges with dealing with multimodal data is that, first of all, we have to obtain a shared representation of the data. And what does that mean? That means that we really have to align together an image and the text, because for a given image, you have multiple lines of text. And then you have to be able, once that alignment process is done, then you have to be able to extract features from that. There's also the issue of translation between modalities, because sometimes what happens is artists represent some portion of the lyrics of the song, but not the entire song. So they feel like, because it's a very subjective process, and they would depict only certain lines of the song as opposed to the whole song. And then what ends up happening is there are gaps, so that the alignment process that I was just talking about may not go as well as you would anticipate. So there is the need, though, of trying to figure out whether we can actually understand what the artist might have come up with should he have wanted to illustrate those lines that he did not in the first place. So we would like to be able to do that. And so cross-modal generation is one way of doing that, and I will talk a little bit about that in a few minutes. So most of the machinery that we use here is basically deep neural networks, but I will begin, and generative models. But before I jump into that, I'll talk a little bit about the modeling process, beginning with the very simplistic minded perceptrons, which are essentially a kind of model that a type of artificial neural network. What the perceptrons do is that they take in a vector of real valued inputs and calculates a linear combination of this input. So it's probably easier if I show you a picture like this. So it takes in a bunch of inputs, and in our setting, these inputs could be either textual inputs or image features. And for every one of these features or inputs, we calculate some weights. And the weights are what we learn from our training procedure. These weights are all summed up, and we then, so we take this vector of real valued inputs, so x1 through xn here are real valued inputs, and it calculates a linear combination of these inputs. So it multiplies each feature by the corresponding weight and generates a weighted sum. If this weighted sum is 1 if the results get greater than some threshold, or -1 otherwise. And this is really how you would use an activation function. And in this case, the figure actually shows the use of a sigmoid activation function. And then it generates an output, and this output is either a +1 or a -1, depending upon what the product of x times w gives you. So this is how a very basic perceptron works. And from this, you can stack up these perceptrons and build what are known as artificial neural networks. So you could have many of these perceptrons stacked up one on top of the other, and then use these as what's known as a hidden layer of these perceptrons as well. And in this case, once you have a really complicated network structure like this, you have multiple inputs to deal with, as well as potentially multiple outputs. The word deep in deep neural networks comes because instead of having one hidden layer like we have here, so if you notice, we only have one hidden layer here, you could then stack up the hidden layers and get many of those, and then you really have a deep neural network going. So what is the idea behind making these models more and more complex from the basic perceptron all the way to the deep layers? Well, the idea is to learn nonlinearity of your data, because you have to be able, if you notice, this perceptron is really a linear combinator. But when you stack them up with various different weights, you get a nonlinear learner there. And the nonlinearity goes even more when you do a deep learner. And this is what is the driving force in our setting, because what happens is, because of the very high dimensionality of our data, where we have both the text as well as the image features extracted, that extreme high dimensionality has to be dealt with in a certain manner. And deep neural networks are, in fact, the state of the art to do that. But what we do is even more than just deep learning. We actually do what are known as deep generative learning. So in this case, what we want to do really, if you recall, we said earlier that sometimes the lyrics are not exactly illustrated or demonstrated by an artist in a paint, in a scroll, or in a panel. And so we do have missing data. Sometimes there are extra scrolls which don't reflect the words of the song. So either way, what we want to do is generate what you would call fake pictures. The artist may not have drawn it, but can we get an intuition on what his or her notion was, or what his thinking was when he drew the other pictures, and from that we would try to infer what he would have done if he knew only perhaps the lyrics of the song, and what would he have done. So for that generating of those fake artworks, we would do what is known as generative learning. And the way this works is that we treat all of the multimodal data as stochastically generated from some latent variable space. And from that, we obtain a shared representation of his understanding of the world. And from that shared representation, we really try to pull out what he would have done if he knew about the places where one of the data forms or modalities was missing. The advantages to this form of generative learning is that not only the multimodal data can be generated from a shared latent variable, so you get an intuition on what he would have done, it also allows you to share this modality across domains, so you can really go for cross-modal generation of your data. Disadvantage is it's a very, very, very slow process. It's very compute intensive, and you have to rely on some really heavy duty computing to be able to get them to work for you. So what we are talking about is really deep generative models, which provides the framework to develop distribution of generative models by deep neural networks. This is the end-to-end learning system, so it does both a forward learning as well as a backward propagation. It has an ability to generate the high dimensional and complex data. So there are multiple kinds of these deep generative models. One of them is what are known as variational autoencoders. The others, generative adversarial networks. In our project, we have mainly tried out variational autoencoders at the moment, but we will definitely move on to GANs as well. And the way these multimodal generative models work is that you assume that you have a data set. Each data set X has a certain M number of modalities. So each point has M modalities. And you essentially want to find out the joint distribution of the multimodal data. You would build a probabilistic model to do that. And you will assume that there is a latent space, Z, that embeds these different modalities. And this ability to actually come up with that latent space and do it well enough is what guides how well we can generate data at some later point. So two most important things in such a problem setting is the ability to share across the modalities and to generate modalities to generate across different modalities. So what does it mean to have a good shared representation of your data across modalities? Well, we need similarity in representation space, and this implies that we want them to learn the same concept. So if you're trying to learn mythology features, if a particular panel has mythology in it or not, and the lyrics of the song also have to be able to learn mythology. So they have to share and be able to learn the same concepts. And it must be easy to obtain even in the absence of some modalities, because sometimes the lyrics will be there, but not the representation in a painting. And so really what you're trying to do is learn a probabilistic model. And for each of the different modalities, you would be able to come up with this latent variable model. And from a statistical perspective, what this means is you come up with a model that has a whole lot of parameters in it. And we are talking about several thousands of parameters, and we try to learn them by a procedure which is known as maximum likelihood. And now this often becomes intractable because executing this large-scale optimization procedure over multimodal data isn't necessarily straightforward. So what we end up doing is either parallelizing our process or distributing it. And that's where the major part of our research really is in designing algorithms that actually scale these intractable procedures. So some of the things that we are in fact concerned with is the design and training of these generative models, and of course, being able to do inference from this latent variable space. In the interest of time, which I know I have run over here, but then I started very late as well, I'll just tell you a little bit about something called variational autoencoders, which I was planning to do. So these are, again, a kind of latent variable models where we use probabilistic learning to be able to figure out what is the probability that what is the how do we maximize the expectation of that data point given the parameters of our model here. So instead of maximizing something very intractable like the log likelihood, we maximize a different objective, which we in this case is called evidence lower bound, or ELBO. And variational autoencoders actually help us solve that. So VAEs present both generation and inference as part of the deep neural networks. They can be trained fast, have representation and learning. And without going into too much of the maths here, I'll tell you two important things about these multimodal deep generative learners, that there are two main categories of these models. One which go by the name of coordinated models, where you are really modeling each of the modalities that we have independent of the others. So if you have audio data or video data, you really build the models independently. And then you sort of figure out a way to merge them and learn the latent space. The other is what we call a joint inference. So you take into account all of our modalities. And so here's a picture for the two methods. So if you look at the figure on the left, the X1 and X2, the shaded round things are really the observed variables. And those are X1 and X2s are from two different modalities, from which we will learn the inherent latent space, which is actually given by Z1 and Z2. And Z1 and Z2, in this case, in the left model, really learn the same latent space. On the other hand, in a joint VAE or a variational autoencoder, you would use both X1 and X2, which is the figure on the right. You would actually use both X1 and X2 to come up with a latent representation. So the joint models are really much more preferable in some sense, because that would help us learn cases to generate what we call either fake text or fake images, because we only deal with text and images as of now. So we are trying out various mechanisms of designing these joint models, and some of the challenges which are well known for joint variational encoders are basically handling of the missing modalities. So how do you want your model to behave when there is known missing data? So you have the panels, you have certain things illustrated, but not all. So there is an issue there. You also want to learn modality-specific latent variables. So if when illustrating, you haven't illustrated all of what you possibly could, because a song is really a mythological song that has been passed down from generations, perhaps, you may not have illustrated everything. And so you would want your model to be able to tell you, well, can you guess or can you imagine what he or she would have drawn, even though he's actually not drawn it? And so it is challenging to be able to do modality-specific learning, because oftentimes learning that shared space is perhaps very hard. So for now, we've been working on two modalities, in fact, and we are at the point where we are expanding on this work to be able to incorporate audio data. We are really not there yet as of now, because bringing in audio to our mix of really compute-intensive tasks will have its own compute challenges. But at some point, we would definitely want our system to give us some ideas on how fast this and how scalable these algorithms are, if one were able to actually integrate all of the 4 different modalities that we have. So it's still a work in progress. We are always looking for experienced programmers who are either Java or Python. Most of our code is in Java. We still use Java for deep learning, and we are very happy with it. We also love Python very much. Lots of coursework, because we have lots of projects for students to do independent studies on a topic of interest. We also like we also work with a team of business analysts, because we are also working with local businesses. And this is also a process to help support our artists. And in fact, some of the artwork is this particular scroll was actually showcased in our by our Office of Educational Outreach, and the graduate school really liked one of these posters. But we do have a lot of scrolls like this for purchase, which actually helps the artist, sponsors their artwork, and also helps to preserve their work in museums and other digitized formats. So the anthropology community is really very curious and very interested in digitizing these works, because A, it's an endangered art form, and B, because it's even the anthropology community has most of these art forms in textbooks and not in a digitized format. So searching there is definitely out of question as of now. So with that, I will end my talk here. And I really sped through several of my slides here because I started quite a bit late. But I do hope that you were still able to follow along, and I'm open for questions. Thank you. Sure.
The next speaker, right? And so you say you took a train to come here from Buffalo?
So I have full disclosure is that I have a
Education.
it's education, yes.
Yeah.
But so